Hello and welcome to Lecture 2, The Chemistry of Biology. If you're following along on the Guide to Biology 101, this is over Chapter 3 in your book, and it has to do with content that will be in Lab number 2 and covered by Quiz number 1. So, carbon is another very special atom. We talked about how water is so important to life. Well, we also wouldn't be able to have life without carbon. Carbon has 4 valence electrons. This means that carbon can make 4 single bonds, 2 double bonds, 1 triple bond, and 1 single bond, or any combination of those. So it's a really versatile piece. It's, you know, it's like those little Tinker Toy wheels that could connect anything to anything, that were like completely useful and you could build wonderful things out of them. I remember that from my childhood. I don't know if you do. But anyway, carbon is awesome. Carbon can form long chains. Carbon can form rings. Most of the stuff in your body is made out of carbon. And that's why carbon gets its own branch of chemistry called organic chemistry. A lot of people here in Oregon call it OChem. We called it Orgo back in Michigan. So organic chemistry is chemistry that deals with molecules made mostly of carbon and hydrogen. These are organic molecules. So obviously if OChem is if OChem is a full year-long course and we're spending 1 lecture on it, we're not going to go into a lot of details. I just want to give you an overview of what organic chemistry is, and how it's going to be useful in the context of our course. So, the most common elements found in organic compounds are, of course, hydrogen. When you make molecular models of things in organic chemistry, they're always color-coded, so carbon always winds up being little black balls. You guys remember our oxygen models from the last chapter? They had a lot of little white hydrogens and red oxygens. Also, nitrogen and phosphorus are quite common. Nitrogen shows up as blue and phosphorus as yellow. So there are a variety of different ways that you can represent organic structures. I'm showing them to you because when you see a picture like this, I want you to know, oh, that's a molecular model. Look, it's glucose. I'm not worried about me giving you the chemical formula for glucose and you drawing this. That's something that when you take organic chemistry or biochemistry, you'll have to worry about. But in the context of this course, I just want you to recognize, hey, this is a chemical formula for something. You can also represent organic structures with rings. So all the C's and H's that were around here are gone, and now you just have a ring. That's another way that organic chemists will show you glucose. And then here is the simple minimalistic way of showing glucose. And you just show the ring as a polygon, and there's a stick because there's a carbon at the end. Again, don't worry about it. Just when you see this, know it's not Pac-Man's cousin, it's an organic molecule. Another way that you'll see, and your book really likes showing it this way, is using the ball and stick model. These are where you have these color-coded beads, and the beads are all hooked together. So there's glucose again. And then you can also use a space-filling model, where you show closer to what the actual shape of the molecule would be. So that looks like you took the previous picture of glucose and you inflated it. So if you see something like this in your book, you go, wow, that's a really big organic molecule. And yes, it is. As a matter of fact, it is hemoglobin. Here's another way of picturing hemoglobin. Now hemoglobin, by the way, that's the thing in your blood that carries the oxygen. It's a protein with some extra bits on it. You can see this is another model that kind of shows you the 3D figure of it. And then here's the ribbon model. So all of this, I just wanted to say, hey, this looks like a protein to me. Okay, so in organic chemistry, you have lots and lots of chains of carbons and hydrogens. and the backbone of all organic compounds are going to be made of carbon and hydrogen. However, you will also have functional groups. Functional groups are clusters of atoms that are not mainly carbon and hydrogen. They've got other things too. These are bonded to an organic compound. They give it special properties. So these are the important bits. These are the bits that are going to do chemical reactions or be charged with something. The carbon and hydrogen are just the structure part. These are the bells and whistles. So here's a chart showing you the functional groups. So you know something exciting is going to happen. If you see an oxygen, especially if it's double bonded, if you see a nitrogen or a phosphorus or a sulfur. Now this is kind of important. A monomer is a small molecule. Your body is a big complicated thing. In order to make your body has taken monomers and made them into polymers, which are many monomers all bonded together. So this is like you start out with a bag of Legos and you make it into something that's useful. Condensation reactions are the reactions that join monomers together to form polymers. So condensation reactions are what you use to stick the little monomers together. Hydrolysis reactions cut the polymers into individual monomers. So to break up a polymer, you use hydrolysis. Here's a picture of it, and then this link here, if you choose to go to it, and I recommend it. This is a nice little animation showing this happening. So here's a condensation reaction. You have two organic molecules here, and when they come together, it gives off water as a byproduct. So condensation makes water. Just like when you see condensation on your shower door, you've made little water droplets stick to your shower. Hydrolysis literally means water cutting. So as this polymer splits into two monomers, it takes water to make the cut. So that's how you remember hydrolysis. Now there are four big types of biomolecules, and these are the ones that we're going to talk about in class. These are what all life is made out of. And these are the carbohydrates, or the sugars, the lipids, the proteins, and the nucleic acids. We'll start first with the carbohydrates, or sugars, or carbs. These are your sugars and your starches. They're made of carbon, hydrogen, and a little bit of oxygen thrown in there to flavor things. They're often found as rings or chains of rings, and you know you're looking at a carbohydrate if it has a name that ends in OSE, like sucrose, fructose, glucose, galactose. Simple sugars are known as monosaccharides. Mono means one, like a monocle is one of those little one glasses you see like fancy British men wearing. Saccharide means sugar, so monosaccharide means one sugar. It's a backbone of 5 to 6 carbons joined together, and they can be straight or they can be in rings, like this little picture. Now, you don't have a lot of monomers out there. Most of the time you have polymers. These short chain carbohydrates, which are a few monosaccharides bounded together, are known as oligosaccharides. For example, the sucrose in table sugar is two molecules bound together. It's a glucose and a fructose together, which is sucrose. So this is why if you're diabetic, you keep little glucose tabs in your purse in case, or wallet or wherever, in case your blood sugar gets too low. It's easier for your body to digest glucose because it's just a monomer. In order for your body to digest sucrose, it has to take the energy to cut sucrose in half. So how are these molecules bound together? Well, it's with a condensation reaction. A glucose meets a fructose on a warm summer evening, and these two parts of them react, and you give off water as a byproduct. Condensation reaction. You also have some very complex carbohydrates. Polysaccharids, which is what they're called, poly means many, are very long chains of polymers, and these can be hundreds to thousands of sugars. Polysaccharids are good molecules for storing energy. That way you can just break off one when you need it. It's like having a whole container of Spree all nice and bound together in a package. And your body can't burn polysaccharids without breaking them into monosaccharids. Just like you can't eat an entire thing of Spree in one mouthful. You break them off one at a time and eat them. Here is a polysaccharide called cellulose. This is what gives plants, like trees and flowers, their structure. You can see each of those little orange things is one individual sugar molecule, and it's kind of bound together into sheets. Here's amylose. This is something that plants use for energy storage. So this is a long starch that's kind of bound together here. And this is, the glue on envelopes is plant-based. You actually have an enzyme in your saliva called amylase, which digests amylose, the sugar. So that's why when you first lick an envelope, it tastes kind of gross, and then it tastes sweet on your tongue. That's your enzyme breaking down this sugar, or starch. It's your enzyme breaking the starch into sugar. There we go. In your own body, sugar is stored as glycogen. So this is in your muscles and liver. When your blood sugar falls, like when you finish digesting your meal, the liver will break down glycogen into glucose for use. And when your body has finished making its glycogen stores, it'll store it as fat. We'll talk about that more later. On to the next class of biomolecules. These are the lipids. The lipids are fats, oils, and waxes. Many lipids contain fatty acids, which are carboxyl groups, which is this little bugger up here. It's a functional group. See, oxygens, it's special. This is attached to a long chain of carbons. Lipids are great sources of energy. This has more energy in it than sugars do.